How is friction included in models of motion? This is the question students explore in Investigation 10D, work done by friction. This investigation has 3 parts. In part 1, students indirectly measure the coefficient of rolling friction for the smart cart. In part 2, students attach a friction block to the back of the cart and indirectly measure the coefficient of kinetic friction between the block and the table. And in part 3, students combine the 2 types of friction and identify when work is done on the cart block system versus when work is done by the system. Open the 10D friction and losses experiment file and connect the cart using Bluetooth. Put the cart on a level surface, start recording data, and then give the cart a gentle push. Stop data recording when the cart has stopped. In the software, use the delta tool to measure the stopping distance of the cart. Students then use that value to calculate the coefficient of rolling friction for the cart. For part 2, tie the friction block to the plunger end of the cart using a short piece of thread. Then place the cart block on a level surface. Move the cart forward until the thread is taut. Then, start recording data and give the cart a push. Stop recording data when the cart and block come to stop. Again, measure the stopping distance of the cart and block system. Students use that value, along with the coefficient of rolling friction from the previous part, to calculate the coefficient of kinetic friction between the block and the table surface. Now that students have coefficient values for rolling friction and kinetic friction, they add a mass to the top of the friction block and then use their coefficient values to calculate a prediction for the new stopping distance given the same initial velocity. Students can find the initial velocity in their data. This value corresponds to the velocity of the cart immediately after it was released. Students test their predictions by recording a new set of data with the mass on the friction block. To find the stopping distance, students should measure the change in the cart's position from where its velocity was equal to the initial velocity from the previous run, to where the velocity is 0. The initial velocity in the previous run here was 0.593 meters per second. So observing this data, we find where the velocity was approximately equal to 0.593. There we go. And then we measured the stopping distance from that point on the position graph to where the position stabilized. This measured distance should be approximately equal to the stopping distance in their prediction. In part 3, replace the short section of thread between the cart and the block with a section about 50 centimeters long. Then move the mass from the friction block to the top of the cart. Arrange the cart so the cart is near the block and the thread is slack. This way, when you push the cart, it will roll freely until the thread is taut and then drag the block until the whole system comes to rest. Now, start recording data and then give the cart a push. Stop recording data when the whole system has come to rest. In the graph, students should identify where the cart is being pushed where the cart rolls freely, the point where the string becomes taut, when the friction block is sliding, and where the cart and block come to rest. Students also identify the area in the graph where work was being done on the cart to accelerate it. And also the area in the graph where work was being done by the system on its environment.